I'm going to talk about residue field domination, but I'm going to, okay, I'll quickly sort of say something about what it's about, and there'll be lots of sort of unexplained terms, and then I'll sort of go and lay sort of the background for this. It's going to have to do with the model theory of valued fields, but I'm not going to assume that people know what valued fields are, although I'm sure many of you do. And then it also has to do with something which has been sort of a recent trend in model theory, which is trying to apply the methods of stability theory in non-stable settings. But I'm also not going to assume any knowledge of what stability theory or stable or non-stable settings are. So as a result, this talk is going to be mostly sort of trying to like paint the sort of picture of where the sort of things that I'm doing my research on. I think I'm not going to go a lot into proofs. And if you are someone who already knows what stability theory is and what valued fields are, you might be very bored. So I apologize. I apologize. There's no guarantee you won't be very bored regardless. But, but if you know about stability theory and valued fields, then the chances go way up, I suppose. Okay, so first let me try to say what a valued field is. This is maybe not the sort of normal introduction to valued fields, but I think this is a nice sort of easy to picture sort of an easy to picture example of a valued field. So let's start with the reals and consider, and we'll make a field extension by giving ourselves a single indeterminate t. And so this will be the field of rational functions with real coefficients. Oh, look, it got brighter. That's nice. How did that happen? Okay, so in any case, negative 1 is not a sum of squares in this field. It's fairly easy to check. So that means that this field can be ordered. And there's an easy way to see how the ordering works. There's many different orderings. There's easy to see at least one way to do this, which is just to say that one element of this field, thought of as a function, I mean, one element of the field is less than another element of the field. When you think of them as functions, it is, let me just read what is there. P of t is less than q of t if for all sufficiently large r in the reals, p of r is less than q of r. So what sort of ordering should you expect here? Okay, can people see when I decided that I should use these would be better. Let's see. People, this is visible too, good. Okay, so first of all, say maybe you just have like the constant function 1. But of course, if I draw the function t, we see that of course 1 is less than t. But of course, in this is you might say a non-standardly large element because in fact t is going to be bigger than any constant. Yeah. But of course, if you have something like t squared, it's yet larger. Yes. So and in fact, it's infinitely larger than t. So okay. So here's an ordering on this field. Let me see if my clicker still works from over here. Yeah. Okay. So
are you saying this is linear, so they don't?
Yes. Yeah. Okay. I was thinking I would.
Just say positive means leading coefficients are positive, right?
It's quotient though. It's rational.
Yeah, okay, but if both leading coefficients are positive, right, or both are negative, or no, is it not?
Yeah, I mean, okay. The way I think about this is, was I going to? My talk is a little bit long, potentially longer than I thought. So maybe I can introduce a few more things than I. So there's an important idea in the model in model theory of fields, that some fields are say O-minimal. And so an O-minimal field is one where in one dimension you can only define things you can define in the order. So O is for order minimal. So you can only define points and intervals. The reals are a real closed field is such a field So you can't, these are definable functions in the reals, so they can't cross each other an infinite number of times, because you could just define the points at which the two functions cross each other, and that would be not a finite union of points and intervals. So eventually, one function has to become, no matter what definable function you have, one of them has to be bigger than the other and stay bigger. So you can see that this is an actual linear order. Yeah. Okay. We are also going to think of, but we are going to make a sort of a coarser order as well. We'll say that two rational functions are equivalent if they are big O of each other. This big O notation, again, maybe I didn't put this on the slide. P is big O of Q if for sufficiently large T, P is less than a constant times Q. Okay, so we can make an equivalence relation by saying P is big O of Q and Q is big O of P. I guess this has a special name. It's like big omega.
Landau symbol.
Lambda? Okay.
Landau symbol.
Landau symbol, yeah. Okay, we can take we leave out 0. This is the multiplicative group of this field, and we mod out by this equivalent, saying two functions are equivalent if they are big O of each other. And what we get is an ordered abelian group. The group structure comes from the field multiplication. So this is the field as a multiplicative group, and you mod out by this equivalence relation. Even though it starts off as a multiplicative group, you might think that you would write the quotient multiplicatively, but it is traditional to write the quotient additively. And this quotient is usually called gamma, and this is a value group. And this quotient map is what's called a valuation, and this is what makes something a value field. Yeah, so traditionally I think that positive valuations would be, positive valuations are given to things that are infinitely small. So we would say maybe the value of t to the n, we could set that to be minus n. We could say maybe I didn't give an example of something which is infinitely small, but of course I could have something like 1 over t is obviously 1 over t is less than 1, but it's also less than any constant function. Yeah, so this is an infinitesimal element. 1 over t to the n, we can say that this valuation is n. Yeah. Okay. So here we have, this is a valued field. A valued field is a field together with such a map.
So in this particular example, the group is Z.
In this particular example, the group is Z. Yeah. This quotient map is called evaluation. I think I said that already. The collection of all functions such that are big O of, I should have said that are equivalent to 1. Yeah, not just big O of 1, but vice versa as well. Is a convex ring. It is we'll call it the valuation ring, and we'll denote it by V. So So for instance, the constant functions are all in the valuation ring, but yeah, okay, let's see, if I draw something like this is 1 plus 1 over t, so this is also in the valuation ring. It's something infinitely close to, it just differs from 1 by an infinitesimal, so it's also
So are those just functions which are eventually bounded, yes?
Yes. Okay. Let's see, the collection of all things in the valuation ring, so that 1 over that thing is not in the valuation ring. Okay, so like 1 over t. 1 over t is in the valuation ring. It's infinitely close to 0. It's obviously eventually eventually bounded, but 1 over it is not. So these form a maximal ideal. And, okay, there's some work to check. I suppose it's a maximal ideal, but it is a maximal ideal of the ring with all these elements in the infinitesimals. I guess I squeezed in one more thing here. Okay, so because we have a maximal ideal, we can mod out by the maximal ideal, and which of course will result in a field. And this is called you can call it the residue map. In this particular case, we've also, because this is like a non-standard field, we could also call this a standard part map. So for instance, the standard part map, so in this example, V mod M is again the reals. And so for instance, the constant function 1 here, of course, maps to 1 in the reals, but so does 1 plus 1 over t. It also maps to 1 in the reals. Okay, I guess I didn't have room to squeeze this in. This is the valuation ring. This is going to be called the residue field. For us, in this example, it is the reals. Okay, that's already a lot of introductory ideas. So there's more coming, but this is maybe, other questions? Yeah, okay. Model theory, we will consider this as a field, first of all. So I introduced it as functions, but we're just going to think of this thing as a field element. So we'll add, subtract, multiply, divide by it, but we won't evaluate it there's no built-in function that lets you evaluate this at something in the reals. Okay, it turns out that this is not a terribly well-behaved field in the sense that there's no good language for which it has quantifier elimination. So that's you don't need to know what that means. One way to make it well-behaved is to take its real closure. I mean, I assume that many of you know. The theory of the reals, the rational, my guess, I do not know. I mean, I know that its model theory is presumably, if it's nice, it should be hard. There's a lot of stuff, there's a lot of old open questions about the complex numbers adjoining T. Is this a stable field? No, everybody assumes that it's not a stable field, but no one has been able to demonstrate its instability. And so it might be that R adjoining T, you can define more things in R adjoining T than the complex adjoining T, so maybe you can easily tell it's bad, but I don't remember this off the top of my head.
Pick out the integers, you're in trouble. Right?
Certainly if you can pick out the integers, you're in trouble. I don't.
Well, just as a group, you're not in trouble.
Yeah, you're not. Oh,
As
you're
a
not.
ring.
As a group, it is a divisible ordered abelian group, which is totally fine. As an additive group. In any case, we don't want to worry about difficult questions about this. We are going to take its real closure. So just to remind people, what does it mean to take the real closure? We want to make sure that all the positive elements have square roots, and we'll ensure that the polynomials of odd degree have at least one root. Just as happens in the real. A polynomial of odd degree, of course, it just crosses the line, right? It starts off, it has to cross the the x-axis, so you see that it has to have a root in the reals. So,
and you make sure there's still an order.
Yeah, okay, that's true. You do have to check that doing this does not somehow introduce a some way of writing -1 as a sum of squares. Yeah, so yes, but it is true. Like if you have an orderable field and you take its real closure, you still have some field that can be given an order. Oh wait, maybe I should just say, so what is this doing? So for instance, how many more things can I add here before this becomes completely impossible to read? Okay. Yeah, for instance, now we have the square root of t, yes. So, and so we have to add new valuations, yeah, because the, because the valuation map is a homomorphism of the multiplicative group structure. So because the square root of t times the square root of t is t, we see that the valuation of this plus the valuation of this has to be, what did I say, SV minus 1. So we will have the valuation of the square root of t is negative 1/2. Yeah, and of course we're also adding cube roots of t and various other things. And so the value group is now going to be the rationals. We started off here as the integers, now it's the rationals. And I haven't actually changed the residue field. I've just added new valuations. So we still have a residue field that is the reals, but now the value group is the rationals. Yeah. Okay. Okay, so we are going to think of we're going to restrict ourselves to real closed value. These are too hard for us. We're going to think of real closed fields. To take care of some sort of model theoretic bookkeeping, I guess, what is our actual language? We are going to have the field structure on this real closed field, and we will have gamma as a sort. It just means like a definable set off to the side, yeah. And we will also add the residue field, which I will denote as k, which is in our case, in this example so far, the reals. And that'll also be part of our model. It'll be also there as a definable set over off to sort of the side, and we'll also add the map from, we'll add these two maps to the value group and the residue field. If we want quantify elimination, I guess we also have to add the order and the addition on the value group, and we have to add the field structure on the residue field.
The order comes from the squares.
Yeah. Well, okay. In this example, the order both on the residue field and the value group is simply inherited from the order on the field.
Yes.
Yeah. Because the
In closed fields, you always have x's.
Oh, I see. Yes. Yeah. I see. The order on here. Yes, is definable because the positive elements are definable. So something is positive if and only if it has a square root.
But you want quantifier elimination also.
Yes. Yeah. Again, I didn't want to get caught up in details of quantifier elimination. So but so to have quantifier elimination here, we need to add the ordering. It is in fact a fact that if the only field that has quantifier, let me back. Quantifier elimination. I'm not quite sure if everybody has the definition of quantifier elimination right at the forefront of their brain. So quantifier elimination just means any formula is equivalent to a formula with no quantifiers. Yeah. The only field with quantifier elimination in the language of fields is an algebraically closed field. So you cannot expect to have quantifier elimination in just the language of fields anywhere else. The only field that has quantifier elimination, if you add a symbol for the ordering, is a real closed field, and that's a complete theory. So, yeah. So of course, here we have a more complicated structure. So we also have the valuational structure. But we do get quantifier elimination in the language of ordered fields, together with these maps, and I guess we have to give, this is a divisible ordered abelian group, and so it should have the appropriate language, in other words, plus and less than. And this is an ordered field, and you can check that this itself is always is going to be a real closed field, so it will have, that part of it will have quantifier elimination in the language of fields together with ordering, so plus times 0, 1, and less than.
So this real closure is unique in the context of value fields?
the real closure is, okay.
In the normal fields, the real closure is unique, isn't it?
Okay, I always confuse myself about this. Is the real closure, I mean, the real closures are always isomorphic,
Yeah.
but you can have two different real closures inside of a, is that true? How can that possibly be true?
I didn't say minimal, I just said. Unique.
No, real closures are,
There, for value field.
yes.
Okay, thank you.
Let's see. Okay, so I introduced this by starting to talk about real, just ordered fields. But you can, if you form a field extension, you can also extend the valuation to that field extension. We could add a root of -1, and adding a root of -1 to any real closed field gives you an algebraically closed field. It's still a valued field, and this is we refer to its theory as an algebraically ACVF, or algebraically closed value field. Technically, I should say there are other algebraically closed value fields, ones that have different characteristics. I'm sticking to characteristic 0 in this talk. Yeah. Okay. Maybe just a couple comments. Even though I introduced them in this order, this is not the order in which people started thinking about them. This is the thing that people started thinking about first. And you can think, there's different ways to think about the valuation other than just this picture. This is not the picture I think that people might have had in their heads for this valuation. Here, the field is not ordered. Right now, as soon as you have a square root of -1, you can't order a field. That's an easy exercise if you haven't thought about it before. So there's no ordering at the level of fields. There's still an ordering on the value group. So here of course, it's an easy thing to think is well, the value group just inherits the ordering from the field. And so you might think the value group here would be unordered. But of course, you can say A is less than or equal to B. The valuation of A is less than or equal to the. I'm not going to use that red. This is annoying red. The valuation of A is less than or equal to the valuation of B. Let's see. Wait, that means A is. That would mean you think of this meaning that A is possibly infinitely bigger than B. So that would mean that B over A is in the valuation ring. So as soon as you have the valuation ring, even though if your field isn't ordered, you still get an order on the value group itself, just because you can talk about well, is B over A in the valuation ring, or is A over B in the valuation ring? And because this thing M, this is really a maximal ideal, you can check that one of these two things has to be in the.
So the valuation group changes as you add the square root of
No. Yeah. So going from here to here, this would be called a ramified extension. You're only changing the value group. Going from from here to here, this would be a residual extension. You only change the residue field. I mean, you change the underlying field too, but you don't. You change the residue field and you leave the value group unchanged. Yeah.
So are we looking at rational functions with complex coefficients now? Are we looking
Wait. You mean you're already, even at this stage, of course, you're no longer with just rational functions with because you have to add roots of. At this stage, I think this is a good way to start thinking about it. But at this stage, I just think of it. The picture in my head. Maybe I should say this. I now just want, we're going to think of the, even at the level of real closed valued fields, we're not going to think of the whole thing as one-dimensional, and somewhere in the center, here we have V, and then right around 0 we have, maybe I'm drawing this too small to see, the infinitesimals, M, and we have the standard part map down to another field, the residue field.
And in the example you gave, the ordering is essentially like the degree of the polynomial.
Yes.
Or minus
yes.
the degree.
Yeah. In the original example, the valuation is just the order of the polynomial, or you could just make it the order of the polynomial. I mean, you could, instead of doing it at infinity, you could do everything as approaching 0, and then you could just make the valuation the order of the polynomial. But this is already taxing my artistic abilities to the utmost. I cannot reliably draw things approaching 0. So, yes, yeah. Okay, so these are the two sort of things which we're doing the model theory of. These are two realms in which you're doing the model theory of: algebraically closed value fields, which we can think of as the algebraic closure of this example, and real closed value fields, which you can think of as starting off with the function field and taking off the real closure, adding square roots and roots of odd degree polynomials. Okay, so, right, as I said, people started thinking about algebraically closed valued fields. And there's a phenomenon that they noticed that they called stable domination. And this looks absurdly complicated, and most of the rest of the talk is just going to be me trying to convince you that it is actually sensible. Okay, so here we get first I have to say what stable is. A formula is stable if it doesn't have the order property. What does the order property mean? That means there's no sequence AI, BI, I less than omega such that the formula is true of AI, B, J if and only if I is less than J. Okay, so that's what it doesn't have to be like a strict order on the entire model. It just, so something weaker than a strict order. There just have to be these elements that you can, two different you have A's and the B's, and you can sort of order them relative to each other.
And these are tuples, the X and Y.
These are tuples, yes. Yeah. But certainly, if you just have an actual, honest-to-goodness linear order sitting around, then linear orders clearly have the order property. So valued fields are not stable due to the value group. Of course, in my original example, it's highly not stable. You don't need the value group. It's just immediately not stable because the field itself is just an ordered field. But in any value group whatsoever, you can always say, in any valued field whatsoever, no matter whether you had an order to begin with or not, you always get this ordering. You can say that one valuation is less than or equal to another valuation if B over A is in the valuation ring. Okay, so algebraically closed, any sort of valued field is outside the realm of stable theories. For a long time, a lot of this sort of model theory that had success in doing sort of algebraic stuff had success because it used, there's a whole lot of theorems about stable structures. There's a huge amount of stuff. This seems like a very weak condition, but there's a very surprising consequences of something being stable. And so you could, this is how model theorists prove things. They showed that something is stable. They could show that slight expansion of something that algebraists had considered was also stable. You could use the machinery of stability theory to sort of imitate algebraic geometry in any sort of stable setting, roughly. And you could succeed in that sense. But it would seem that valued fields, you couldn't do that because they're unstable. So, but Haskell, Hrushovski, Macpherson noticed that there's something called stable dominance. That there's a way in which stability worked its way in. Okay, what is it? Okay, so if if you have two algebraically closed value fields, and each of them contain a maximal algebraically closed C, and I am going to just, there has to be some limit to how many definitions I give you, so I'm just not going to tell you what maximal is. If you're very curious, I can tell you at the end, but for the moment, just think of it as it has to be big in some way.
C is a subfield.
A C is a subfield of L and M, and if you have the residue field of L algebraically independent from the residue field of M over the residue field of C, that means that if you have any algebraic relation, if you have two things here that satisfy some polynomial with coefficients from here, they already had the satisfied polynomial. You don't get any new algebraic relations by adding things in, by adding parameters from here. This is called, you can call this algebraically disjoint. In this case, it's also equivalent to being linearly disjoint, if that rings any bells from like algebra classes. In any case, it's a way of saying that they are somehow independent of one another. And I'll say a little bit more about that, even though I won't get into the algebraic side of it. And also that the intersection of the two value groups is just the value group of their common subfield. That's another way of sort of saying that they're independent of one another. Okay, so if you have this, then the type of L over the maximal field C, together with its value group and its residue field in this ground value group, implies the type of L over, oh, I have a pointer. The type of L over its residue field and value group implies the type of L over the other thing. Yeah, okay. What does this have to do with stability? This is like an impenetrable like collection of symbols. I'm going to try to make it less impenetrable.
So C is the intersection of L and M, or could that be bigger?
No, this requires that C is the intersection of L and M, but this is a stronger condition. It is a stronger condition than just being the intersection. You could have C being the intersection of L and M, and you could still have additional algebraic relations.
But you're not talking about the type of a tuple, but the type of an entire field?
Yeah, okay, that's right. I have to remember that this is one of the things that I had to get over when I started thinking about this. Like people just like, it just, you can think of the field as an infinite tuple if you like. And then this just means all the formulas. This means all the formulas indexed by, this has some infinitely long string of variables, and just all the formulas that have parameters from C, from the residue field with parameters from L, all these formulas true about L imply all the formulas true about L, even with parameters coming from some different field M. Okay.
Actually, so there is. So if you take a finite tuple from L.
Yes, it is. By compactness, this is just equivalent to saying the same thing, but one finite tuple from L at a time. Yes. This is called. Okay, this is equivalent. One can easily prove the thing which they called stable domination from this property.
So what dominates what here?
Okay. This would be, okay. That's a good question, and somehow I failed to anticipate this question, because this is not, what they would say is that in this structure, the residue field dominates the field over the value group. But in order for that phrase to make sense, you have to give the equivalent definition, which I am not giving because this one is going to be slightly easier to explain. Even though this one looks hard enough, it's slightly easier than the one that.
You're trying to say the thing is stable if it weren't for the value group.
Yeah, okay, yes, yeah. This is the, that's not really, in a way that's false, but that's definitely the philosophy. The philosophy, and I will get back to that, the philosophy would be like, somehow this means that once you pin down the valuation, then that somehow, in a certain technical sense, which this is approximating at least, that removes all the instability from the structure. Yeah. Okay. Yeah, let's see. So, yeah, so I say not stable. However, why the however? I have to explain at least a little bit about stability in order to explain why. And what is an independence relation? What is an independence relation? Okay. So stability theory is about one particular independence relation, but there are multiple possible independence relations. One tends to write them like this, and you would read this: A is independent from B over C. And the idea is that B and C together contain no more somehow interesting or important information about A than C does alone. So, I mean, it contains some more information, but somehow not important information. So basically, you don't learn anything worth learning about A by also finding out how it relates to B. Okay, so let's go through some basic examples, some algebraic examples first, and then I'll do an easy to draw example. I don't know, maybe I should have done the easy to draw example first, but this is how my slides are, so we're sticking with this. Yeah, okay, so let's think of, I guess I can, right, so maybe here we have a vector space as a subset of here's the vector space, and then we have maybe two other points, B and A. Yeah, they lie in the same, oops. Consider two other elements, A and B in the same coset that themselves are the same coset of V. Intuitively, somehow B should tell you more about A than you could say without parameters, right? If you know here, if you just know about A, it's just somehow sitting outside of V. But if you know B as well, you can sort of see that it lies on this parallel line. In particular, with the parameter B, you can say x minus B is in V. And this is a formula that's true of A. And not only that, if I have, what do I start with, B2, B3, if I have other parameters chosen from other cosets, the formula x minus B sub I is in V define these parallel, in the picture, parallel lines, pairwise disjoint sets. Do I have one more thing here? We call this particular way of getting more information, we call it forking. So we would say A forks with B over, in this case, the empty set. Oops. Yeah, and we would say that this formula, x minus B is in V, is something which divides. Okay, another example. If you take a tuple A in some three-dimensional, say, in the complex numbers cube, so in 3 space, and it's not in any algebraic surface defined over the rationals, over the algebraic closure of the rationals. Well, if you have some surface containing A, that you can define not over the rationals, but some other parameter set. Oh wait, this should be a capital B. Then it seems reasonable to say that capital B has more information about lowercase a than is available over the empty set, and this would be an example of some as yet unspecified independence relation. If then perhaps you have no curve defined over B that contains A, but you do have one over C, a bigger set than B, then you would say that A is dependent with C over B. In other words, you get even more information with C. And you could go one further step and you could then define A precisely, but like every time the dimension of the set which contains A, the definable set which contains A drops, and so you somehow are getting closer and closer to A. There's not an infinite amount of times you can do this. In this case, you can do it 3 times. Okay, so in other words, here we can define, let's make this now a definition. We can define A is not independent from C over B to mean that there's a tuple of elements in A, which is contained over C in a variety of lower dimension than over B. Here it should either say BC, or I should have said that C contains B. Yeah. Okay. It turns out that this is not a different independence relation from the last one. It turns out this is the same one. This is another example of so-called forking. And so we don't need to come up with some new symbol. This is just a symbol for forking. We can say that A forks with C over B. Okay. Let's do an example where you can really see the definition at work. Let's say that E is an equivalence relation with infinitely many infinite classes, each of which is infinite. This is my picture of this model. Each of these, this is an equivalence class, this is equivalence class, equivalence class, equivalence class. There are infinitely many of them. Each one of them contains infinitely many elements. Okay, so let's see. To say that, let's look at the set of things equivalent to B1. That's this set. This set is equivalent to B1. It includes A, and if I move B1 over here to B2, to B3, to B4, I get pairwise disjoint sets. That's again an example. That's essentially the definition of dividing. And so we would say that this formula divides over the empty set. In other words, I can replace its parameter by essentially identical looking parameters, and I get a bunch of disjoint sets. So that's dividing. And because of that, because I have a formula which divides, I say the type of A over B forks over the empty set. Here's the definition. The formula divides if there's a sequence of B sub i's such that the formula gives, they don't have to be pairwise disjoint, just that k of them have to be inconsistent. So you can't always get, pairwise disjoint would be 2 here, 2 inconsistent, that 2 of them don't overlap. But so for some k. In all the examples that we're going to, it's hard to come up with an example where you need a k bigger than 2. Reasonably hard. Right. Yeah. A type forks over C if it implies, well, a disjunction of formulas which divide over C. Again, you can actually, once you make this definition, in almost every example that you can think of, you can drop the disjunction and just say a type forks over C if it contains a formula which divides over C. Okay, so every example of independence relation so far has been non-forking. Non-forking is written like this, and yes, so that's forking. Non-forking is best behaved in theories that are stable. Just to remind you, that means no formula has the ordered property. In these, it is, yeah. There's certain things that you should expect from an independence relation, which I didn't write down. But they're just the common sense things that you should think if that when you have about information, like if a bigger set tells you more information than a smaller set, if you take a yet bigger set, it also has to give you some more information. Various things.
Or you don't have symmetry?
You can say, well, if you insist that there is a limited amount, if you insist that there's a limited amount of relevant information, that you cannot get chains of forking of arbitrarily large cardinality in a large saturated model, then okay, I haven't told you all the things that make an independent relation, but if you assume these things, then you also can prove symmetry. Yeah. Although symmetry isn't really intuitive from the definition of like information, like just because, yeah, here, right, we can see it. Here, this means, here we should think of this meaning B tells you some interesting information about A. Why should it also be the case that A tells you interesting information about B? That doesn't seem like that's just built into the definition of interesting information. You can see that it does here because equivalence relations themselves are symmetric. In a stable theory, telling you interesting information is a symmetric relation. You want to do this? Okay. Right. I did not draw. I meant to. Here we have the picture from. This is just the picture from a couple slides ago, but I need to be still up here. Okay. Yeah, okay. So here, for instance, we have A is free from B2 over B1, for instance, just to give an example. What does this mean? It means that what does B2 tell you about A? Well, it tells you that A is not equal to B2, and it tells you that A is not equivalent to B2, but there's somehow no shortage of facts like this. Like, this A is not equivalent to as many things as you would like it not to be equivalent to. So that doesn't somehow count as, that doesn't give you dividing, so it doesn't count as interesting information. Okay, notice that the type of A over B1, if you think of what's the type of A over B1, it's just everything in this equivalence class except B1. You think of it as a set. I will go back and forth between thinking of sets as collections of formulas and sets as, and types as collection of formulas and types as the sets of elements that realize those formulas. So this is the type of A over B1. What is the type of A over B1 and B2? It's just the same thing. So we can just tell from the picture that the type of A over B1 implies the type of A over B1, B2. Yeah, and this is characteristic of stable theories, that the type of there's a unique extension to there's a unique extension of types to things that you don't fork with. After you here, algebraic closure is trivial. So there's a unique extension. Technically, you need to take the algebraic closure of the bases. But there's a unique extension to stuff that you don't fork with. If you have any independence relation with this property, that there's a unique extension, right? You already know everything that you need to know about A. Forking is the only the forking is the only independence relation that has this property, and it only occurs in stable theories. So when I say it characterizes stability theory, I really mean it. It's the only independence relation that has it, and it only happens in stable theories. Yeah. Okay, so let's see. I think that's what I just wrote here. If A is independent from B over C, unfortunately in my picture, I guess, my picture, this is B2 and this is B1. But okay, if A is independent from something over C, and okay, there are conditions on C. For instance, maybe I want to make C a model. Then the type of A over C implies the type of A over B and C together. Here, there's none of those conditions come into play. Here. Okay, this is the however from many, many, many slides ago. Maybe it's worth going back to the however. Yes, okay. Valued fields, not stable. However, if you take some parameters, here this M is sort of like our B2 here, in the sense that it's going to be free from our original thing, or not independent from the original thing. So here this is independent from L. How? In the sense that the residue fields are independent, and this sort of sense that the value groups are also independent in this sense. And what do you get? You get a unique extension of the types. This type implies that type. Okay, so that's where the however comes from, because this is a sort of behavior which is supposed to exactly characterize stable theories. Okay, notice that it doesn't happen in full generality. Like there's lots of restrictions. I haven't even told you what maximal is, but that's a restriction. And then it's not just for any sets. Here you need like residue fields and value groups, and in particular importance you have to have the value group here. So it's not without restrictions, which is why it doesn't somehow prove prove something wrong, which is this is stable. But it is exactly it's a limited form of the thing which should only occur in stable theories. Okay. Yeah. Unique non-forking extensions. Oh, I didn't need to go back. Okay. Well, yes. Okay. That's what I just said. You get independence in a certain sense, and then you get this implication of types. Okay. Actually, I have to say a little bit about what does go wrong when there's an order, right? Because this is only supposed to only happen in stable theories. Stable theories are things where there's no order. So something should go wrong when there's an order. Let's think of the simplest possible order to picture, which is a dense linear order, and then we should see lots of things going wrong. And we do. Okay, so let's think of a particular formula. Here. Wait, how much time do I have left?
Till 6.
Till 6?
Probably more than you need.
Okay. Yeah. I'm going slower than I thought, though, so I do have to pay somewhat attention. Okay, so here we just have a definable set as an interval. We can, just like we have a definable set which is an equivalence class, and here we could just like slide the equivalence classes, they're disjoint, so you get dividing. Here we can slide these intervals down, and they're disjoint, so we also get dividing. But, so this formula divides over the empty set. But look at what this formula defines as a definable set. It is itself a dense linear order. So we can take a smaller interval inside there, and we can repeat this process. And we can just do this as, this is also a linear order. I mean, we're working in some, we're not actually, here my picture I said was of the rationals, but we should be thinking of some larger model of the rationals, some large saturated structure, some large saturated model of the rationals. So in the rationals, you can only do this countably many times, but in some bigger model, you can do it as many times as you feel like, and if you felt like doing it more, you could just build a bigger model. And there's no limit to how many times you could do this, other than like given by the cardinality of the model that you happen to be in. Okay, so in that sense, because this information is so somehow unlimited, we can't really, in that sense, maybe it's not interesting. right, is somehow you can't be constantly surprised by information that has no limit of. So okay, so in that sense, so dividing is, again, I haven't told you what an independence relation is, but one of the things about an independence relation is that you should only be able to have a chain of non-independence, which is bounded by some cardinality, some cardinal independent of the model you're choosing to work in. Yeah, so there's no end of the information that you could have about an element, so it's not, forking is not an independence relation here. Okay, before we go on, I have to point out, let's see, I can erase this. No, not the rationals. Let's take some bigger structure. Okay, it doesn't really matter. Here we have some A1, A2, A3, into collectively A, and here I have B, and so the type of B over A, what does it say? It just says B is bigger than the things in A. That's all it says. Being bigger than is not contained in any interval. It's contained in a half open, right? So you can't slide things over and get disjoint sets. And so in fact we have B is forking independent from A over the empty set. Yeah, so this is now if I choose some, and so the type of B looks like this. If I choose some independent thing, maybe I choose something here, C, we even have that B is free from C over A, because again, it's just, in this case. Okay, the type of B over A is this circle, but the type of B over C is smaller, right? Because, so the type of B over A does not imply the type of B over C. And you can see that this is going to happen whenever you have an order, an infinite order, of course. Okay, so orders stop you from having limited amounts of dividing, and also whenever you have an order, you're stopped from having unique extensions to non-forking set. There's no longer a unique non-forking extension. Here we have two non-forking extensions, or three, right? You could extend the type of B to being over to C. It could be equal to C, it could be over here, or it could be there. Well, okay. Okay. The idea of forking is it gives you some way of talking about dimension. It gives you some way of talking about something like geometry. But of course, in the reals, there's no problem thinking of dimension or geometry in the reals. Our intuitions of dimension and geometry come from the reals. So it's a little weird that you don't have a nice, that somehow model theory doesn't give you a corresponding notion. Okay, we would like a definition similar, we'd like to fix this problem. We'd like to have some nice way of talking about independence that's not ruined by orders. This is the symbol called thorn. So this is something that I have worked on. And so I've been trying to work out various properties of this thorn forking. What is thorn forking? It's just going to be a more uniform, this is the same definition of dividing, except you don't get to, in dividing, you just got to pick whichever parameters you wanted. Here, you're insisting that you have a definable set full of parameters. So it's uniform dividing. Okay. That's what you should think of. The witnesses to the inconsistent sets, like these things here, where before you saw to pick this one and this one and this one, as you will, now you need to have a definable family from which to choose them. Okay, and you say the same definition, type Thorne forks if it implies a disjunction of formulas which Thorne divide. Is it getting too dark? Should we open up some window? Which window should I open that will at least... Is everything still visible but now it's better?
Yeah.
No?
Doesn't help this.
It does not help
It did
this.
not hurt that.
Is this still visible?
Still
Sort of? Okay, we'll go with this. Yeah, okay, so a type Thorne forks over C if it implies a disjunction of formulas which Thorne divide over C. Again, you can sort of ignore this. The type contains more information if it contains a formula which Thorne divides.
So in this definition of Thorne divides,
Yes?
the difference you said is this theta.
Yes.
And what was the previous definition?
Yes.
Of the
Let me go back to the previous definition. Here. Here you have parameters, but you just get to pick an infinite collection of parameters.
Yes.
Here, same definition, except
Oh, the set of parameters.
the
has
set
to
of
be
parameters has to be an infinite definable set instead of just an infinite set. Yeah, so just a tweak in a sense. Okay.
But if you have a set which is k inconsistent, any superset is also k inconsistent.
Yes. No. No.
K inconsistent.
No, wait, I have a picture.
Okay.
Okay. More uniform version. You write it in the same fashion. You say A is Thorne independent from C over B to indicate non-Thorne forking. And now to the picture, which hopefully answers your question. Let's go and see how it's not ruined by this. So, okay, you start by thinking, okay, here we have an interval. We can get a disjoint interval. But I need an entire definable set of these endpoints. And so any definable set that includes this endpoint and also these two endpoints over here will also contain endpoints like this red one and that red one. Right? Because I can't just say I want this one and I want this one as left endpoints, but I don't want this one. Instead, I have to choose a definable family of left endpoints and a definable family of right endpoints. So it's a bigger set, but it's no longer here it was too inconsistent, but now it's no longer too inconsistent
So two
because there's
inconsistent
overlapping.
means actually any two are
Any
disjoint.
two are.
And
K inconsistent means any
Any
K.
k would be disjoint.
Yes.
And
Yes.
if you add things, then you'll hurt.
You can, yes, exactly right, yes. Yes. Yeah. Okay, so this formula does not Thorne divide.
So that's
And-
because essentially there are no definable sets. Essentially true.
Okay, yeah, I guess. This
Except
set
for
does
all
not
the
even, okay, if we went back to the real closed field that we started with, these would also not Thorne divide in a real closed field, because real closed fields are O-minimal, and the only things that you can define in one variable are just points and intervals. But there's lots of definable sets in more variables. There's just not any in one variable. So I wouldn't say it's things like this argument for non-Thorne dividing in one dimension works in anything O-minimal here, not just this. Yeah, not just this. Yeah, when there are some models in which you have this sort of independence has all the properties of an independence relation, which I still haven't told you what they all are, but they're just the nice ones that you think that should come from giving information about something. And then these theories are called rosy, and that includes not only all the stable things, but it also includes things that have orders, like this, but more complicated things than this. It includes everything that's O-minimal, like real closed fields, not real closed value fields. and O minimal things are still like the sort of bottom of the complexity of rosiness. So it goes well past that as well. Let's see. This is maybe a little bit of an aside. If you just look at this picture, which is, I guess, also here, it looks like you're not going to get any Thorne dividing here as well. Right, where did you get dividing before? You got, say, dividing from here, equivalence divided, being equivalent to B1, B2, B3. But you can't do that anymore, because if you just try to take a definable set of parameters, you're going to ruin your disjointness again. Here there's a fix. I'm not sure how many people have dealt with this structure called MEQ. It just means add definable quotients to your model. So that would mean that, like, down here, we would add, you know, just a line where each one of these equivalence classes maps down to a different point on the line, right? So that's that. MEQ is where you add a new sort for every single quotient by a definable equivalence relation. Well, okay, if you're willing to do that, which I think in model theory many people sort of find that going from M to MEQ is sort of a minor step. Although that's, I mean, in abstract model theory. In people that work in like particular concrete models, this can be a very, because like, okay, here you can sort of see what the definable equivalence relations are. There's just the obvious ones. But what are the definable equivalence relations in some more complicated model? That can be a hugely complicated question. It can be harder, it's in general harder than quantifier elimination to figure out what all the definable quotients are. But okay, if you're not going to be worried about the nitty-gritty algebraic details or something, then this step, you don't lose any. You don't really get any more. You never get any more definable sets in your original model. None of like the big sort of picture properties of this model change. Like the saturation doesn't change, stability doesn't change. Everything sort of stays the same. So if you're willing to do that, then Forking and Thorne Forking coincide. So then it's a real generalization in a stable theory. Okay. So why am I even bringing this up? Hopefully, let's see. Oh, wait, one more fact. In any theory, stable or not, non-forking is always the strongest independence relation, and in any theory that has any independence relation at all, Thorne forking is an independence relation in that theory, and it is always the weakest one. So forking is always the strongest, non-forking is the strongest, non-Thorne forking is always the weakest. Yeah, okay. And so maybe you think that the way this is going to go is that, aha, we can use this better thing on ACVF. No, unfortunately, that's not the case. Valued fields are an ultrametric. Oh, I don't have a little bullet explaining that. If you look at, say, everything within a ball of rate, what did we say this was the valuation of this? I think we decided the valuation of 1 over t was 1. So you can look at everything within a valuation of 1 of the, it's a little complicated, 2 different ones. Okay, but there, I started pointing at it, I should go ahead with it. You can look at the ball of radius 1, in the sense of the valuation, around the number 1. So it includes 1 itself, it includes this, but if you think about it, it's an equivalence class. Or if something is within valuation 1 of this, like if you take something within valuation 1 of that, it's again within valuation 1 of the original thing. So any 2 points inside the ball are centers, essentially. Yeah, so that gives you refining equivalence relations, and that ruins Thorne forking in the same sense that orders ruin forking. So that means there's no independence relation at all. Again, I haven't told you what independence relation bit of a cheat. There's no independence relation in algebraically closed valued fields. Not just non-forking, there's none. Yeah, okay. So on the other hand, this thing about the fields being algebraically disjoint, that turns out that's the same as the fields, the residue fields being forking independent. And what I said about the value group of L intersect the value group of M being the value group of C, it turns out that that is just these two things being Thorne independent. Oh, and of course, this is a stable structure. The residue fields are stable, so I could just as easily have put a Thorne forking here. So what's happening is if you take the residue fields and they're Thorne independent, or even just independent, and the value groups are Thorne independent, then you get this unique extension of types, which somehow is characteristic of stability theory. Okay, so that's, okay, so philosophy, which is what you said very much earlier. Once one controls for the value group, it's one stable structure sitting on top of another one. So the residue field is stable. It's an algebraically closed field. That's a stable field. And it's sitting on top of, and then the big structure is also an algebraically closed field. Okay, so, right. When Udi and Deirdre and Dugald were thinking about this, of course, they didn't think of Thorne forking here. That's sort of what I'm thinking about. So I noticed this, and I wondered if something similar should happen with real closed value fields. Can you also get somehow something similar there? So the idea might be that after accounting for a value group, a real closed valued field is an O-minimal structure. That's these nice ordered structures where you only get finite unions of points and intervals in one dimension, sitting on top of another O-minimal structure. Because both the big field, the actual valued field, is as a field, it's a real closed field, and the residue field is also a real closed field. So you might think that there should be some way in that it's just one O-minimal structure sitting on top of another O-minimal structure. And that would have been like some sort of interesting thing if it turned out to be true. So I'm going to try to show you that something even like a little bit more interesting. That would be sort of interesting, but it would also be just like, let's just move all these definitions to a slightly new setting. I'm going to try to argue that in the end, something more interesting is true. So what would this idea translate to in something more specific if you take a maximal subfield of some big real closed value field, and it's a subfield of both L and M, and if the residue field and value group are independent, the residue field group of L is independent from the residue field and value group of M over C, independent in the sense of Thorne independent, then, okay, you shouldn't really expect the type of L over this piece to imply the type of M. Why not? Because of this. You don't get order ruins unique extensions. But you can hope that the only thing going wrong is just the order. Yeah, so all you would have to do is talk about the order type of L over M, and then you wouldn't have to know anything else to get the entire type of L over M. Yeah, so that would be one O-minimal, that would be what I would describe, one O-minimal structure sitting over another O-minimal structure, that this type together with just the order type should give you everything. Because in an O-minimal structure, it's like, that's all there is. It's just the order type, essentially. Okay, so finally, now I can say what our theorem is. Well, okay, when we worked out all the things, it turns out that this type, you don't need the order type. This type just implies the complete type of L over M. Oh, maybe I didn't put the philosophy. Wow, that's a bad thing to leave out. Okay, so what would be sort of the philosophy of this result? Why is it maybe more interesting? This would say that a real closed valued field is something, after you account for the residue field and the value group, there's no more instability. So in a way, it's like a stable structure sitting on top of two O-minimal ones. So, in other words, it should be possible if you understand, if this is like a nice minimal structure that you understand, maybe it's just the reals, and this is maybe just, could just even be the rationals as a ordered group. Then all of like the bad unstable things are just there, and these things that you probably have a better handle on, and then there's the rest of everything should be like stable. I think that's sort of the philosophy that this result seems to say is true. Okay, so that's the result. I'm not gonna, don't worry, I'm not about to like go through a proof of it. I will say just a couple more things. I will say that in doing this, we also know what Thorne forking looks like in either one of these structures. As long as you have a maximal base, Thorne forking is just determined by the value group in the residue field. And in fact, not only that, we can do the same thing for forking. It's just determined by the value group in the residue field. Okay, I say that this is our theorem for RCDF and ACDF. I think that if Udi were here, he would not be like shocked. Like he didn't write anything like this down, but I don't think it's probably thought it was clear or something. So I don't know how much credit I can take for this, but okay, yeah. Right. Okay, that's, let's see. Maybe I should just say a little bit, again, I didn't want to, what we worked on most recently is that it turns out this is not just true for real closed valued fields or algebraically closed valued fields, but any Henselian valued field, as long as the field and the residue field have characteristic 0, that's equicharacteristic 0. The field and the residue field do not have to have the same characteristic. And as long as the nth powers are of finite index. Henselian basically means that if you have a polynomial with a solution over the residue field, you can lift those solutions up to the main field. So if you can solve some equation in the residue field, you can lift the solution up to the main field. Okay, I didn't want to really give a definition of Henselian or yeah. So anyhow, when it turns out it's not just about real closed value fields, algebraically closed value fields. That's a result of myself, Haskell, Jana, and also Pierre Simon. This is just the same theorem as before, but instead of real closed value field, I put Henselian valued field. Equal characteristic 0, the n powers are finite indexes. Okay, that's it. Thank you.
Are there any questions for Clifton?
So how optimistic are you about this kind of portability and stability notion? So it's like stable over an unstable substructure. There's no general theory.
Yeah, there's no general theory. Like, I think that this is like an area of model theory that there are now lots of, okay, this is, I don't want to say that this is a super important result at the forefront of model theory. No, it is not, I don't want to claim it's a breakthrough, but this is like, there's lots of results like this happening in model theory right now. Like, there's all these conferences on what is now being called neo-stability theory, which just means like using stability theory in non-stable settings. And so there's lots of individual results like this, which I think are maybe starting to be formed into some bigger picture, but I don't know if it's quite coalesced into one thing yet. So is there some bigger phenomenon of which this is a special case? Probably, but I don't quite see what it is.
Years ago, stability was being pushed as a good property. While at the same time, minimal theories were extremely active and important. So clearly stability was not the end of the story.
No, it wasn't. It wasn't. Although, like, yeah, like, it is like, I mean, but it's, for instance, like Hrushovski's work on like Berkovitz spaces, like that comes, which I do not ask me to to summarize that, but like there you take, this is essentially what came out of the algebraically closed valued field things, and there are these things called Berkovich spaces that algebraists have been interested in, and it turns out that these are just the space of stably dominated types. And once you know that, then, and this is like stability, even though it's not a stable setting, this is again the original definition of, I mean, it's stably dominated in this sense, where you get some actual non-forking in there. And then you can manipulate that to prove things that are interesting, like contractibility results that had resisted the algebraists' attempts to prove them. So yeah, so even though like it's somehow like, I think a trend recently has been the old stability has been creeping into non-stable settings. Even things like, even into minimality, like sometimes knowing like which formulas are the like forking ones, or if you have a sequence of really non-forking things in an O-minimal structure, if you can understand these, then you can find out more stuff about the O-minimal structure. Sometimes.
We never once said superstable, which is a big role in classification theory, but I guess not here.
Well, okay, I sort of felt like I was giving people enough definitions as it was. Yeah, stability is not just one thing. There's stable, there's super stable, and even better than that, then there is omega stable. And all the things that are stable here are in fact in the nicest category. They're even better than omega stable is strongly minimal. Omega stable of rank 1. And so these were all like algebraically closed fields. Those are omega stable rank 1, degree 1. So I could have said super stable, but I decided I was saying enough things. So,
Vague question. I have this vague map. I mean, there's the non-stable theory. I mean, there are somehow these two reasons for being non-stable, right? One is to have an actual order somewhere, and the other is this independent stuff.
Yeah.
So your theories are they on the good side of the dependent?
Yeah. Okay. This is another thing which is really important, and which I just decided I should leave out. The order property, I've been drawing it like a linear order, but like the order property can come two ways. It can come, like if you have, what does an order property look like? Here's maybe the A's, and here's our B's, and it just means that you have something that looks like this, a configuration that looks like this. So the B's are not connected to anything earlier in the list. Okay, so you can obviously, does this happen inside of a random graph? Of course it happens inside of a random graph, because any particular graph you like to draw happens inside of a random graph. So a random graph also has the order property, even if it doesn't have a linear order sitting inside of it. So these are the two ways that you can either have something in a way it looks like the random graph. In sort of a technical sense, you can have two sets where you can have sort of a bipartite random graph between them. That's called the independence property, or you can have a strict order property, which is what I was drawing. Forking still behaves nicely inside the random graph. So I said like the set of things where Thorne forking behaves nicely is rosy. The set of things where forking behaves nicely is not stable. It's bigger than that. It's simple. So it includes things like the random graph. It includes things like the random graph. Even though the random graph has an order property, the random graph does not ruin forking. So things that don't have random graphs sitting inside of them, or people call them NIP, or not independence property, which I find very annoying because independent already means not dependent. But it stuck. So as much as I try to call them dependent, everybody else calls them NIP. So NIP theories also have lots of nice properties. and including, like, these are the theories in which somehow, even the unstable ones, the forking, there's been lots of work on finding how forking behaves in NIF theories, of which every single example that I talked about today was a quote-unquote NIF theory.
Which means
Yeah. Non-independent property.
Not having the random graph.
Not having a little bipartite random graph hidden somewhere. Okay. Is there anything else?